Hi everyone, we are from Group 6, Thermodynamics and Material Engineering Laboratory. We would like to explain about the explication of first and second law of thermodynamics. Our group consists of Sri Anlaki Nagendra Rao, Tanpik Lin, me myself Devaraj Anlaki Ravi, one Izni Fazila binti Azmi and Zafran bin Zainal. In this experiment, I would like to present about the abstract and introduction. Abstract. The first law of thermodynamics, also known as law of conservation of energy, states that energy can neither be created or destroyed. Energy can only be transferred or changed from one form to another. For example, turning on a light will seem to produce energy, however, it is electrical energy that is converted. A way of expressing the first law of thermodynamics is that any change in the internal energy of a system is given by the sum of the heat that flows across its boundary and the work done on the system by the surroundings. This law says that there are two kinds of processes, heat and work, that can lead to a change in the internal energy of a system. Since both heat and work can be measured and quantified, this is the same as saying that any change in the energy of a system must result in the corresponding change in the energy of the surroundings outside the system. In other words, energy cannot be created or destroyed. If heat flows into a system or the surroundings to do work on it, the internal energy increases and the sign of Q and W are positive. Conversely, heat flow out of the system or work done by the system on the surroundings will be at the expense of internal energy and Q and W will therefore be negative. The second law of thermodynamics says that the entropy of an isolated system always increases. Isolated systems spontaneously evolve towards thermal equilibrium, the state of maximum entropy of the system. More simply put, the entropy of the universe, which is the ultimate isolated system, only increases and never decreases. A simple way to think of the second law of thermodynamics is that the room, if not clean and tidied, will invariably become more messy and disorderly with time, regardless on how careful one is to keep it clean. When the room is clean, its entropy decreases, but the effort to clean it has resulted in an increase in enthalpy outside the room that exceeds the entropy lost. Next, introduction. Experiment application of first and second law of thermodynamics, basically a study of heat transfer in a system from higher heat region to lower heat region. The main objective of this experiment is to prove the first and second law of thermodynamics. We know that chemical system can either absorb heat from their surroundings if the reaction is endothermic or release heat to the surroundings if the reaction is exothermic. If two objects at different temperature are brought in contact with each other, energy is transferred from the hotter object to the colder object until both objects are at the same temperature. There is no net heat transfer once the temperatures are equal because the amount of heat transferred from one object to the other is the same as the amount of heat returned. That's all from me. I'll pass it to the next person.
Hi, my name is Sri Son of Nagendra and I am going to explain about the theory of this experiment. So basically the computation of the heat transport is based on the first law of thermodynamics. It is utilized to investigate the links between different types of energy and their interactions. The net change in the total energy of the system during a process is equal to the difference between the total energy entering and the total energy leaving the system during that process, which is defined by the first law of thermodynamics. So we know that energy in subtracted by energy out is the change in the total energy. We also have an equation where Q minus W equal to delta U plus delta KE plus delta PE. These symbols represents where Q is equal to heat transfer, W represents work transfer, delta U represents the change in internal energy, delta KE represents the change in kinetic energy, and delta PE represents the change in potential energy. So for a closed system, we know that W, delta PE and delta KE is equal to 0 because we have in constant volume. If there is a constant volume, therefore there is no work boundary and the change in kinetic energy and potential energy will be negligible. So the equation that I stated before will become Q equal to delta U. Delta U is U2 minus U1. So the energy balance was utilized to calculate the heat transport in this experiment. We presume that there was no heat transfer or heat loss to the environment in this experiment, and that the cold water gained all of the energy lost by the hot water. Only internal energy exists in this operation because the system in this experiment is immobile. This system energy balance is as follows, as where we have stated before, energy in minus by energy out is equal to the change in the energy system. So from the first law of thermodynamics, we know that energy system is equal to 0. Delta internal energy system is equal to delta hot water plus by delta U cold water. So therefore the delta system is equal to 0. The delta internal energy system is equal to 0. Then we have an equation where mCp times by T2 minus T1 hot water plus mCpT T2 minus T1 of the cold water, which is equal to 0. So the second law of thermodynamics is used to determine the theoretical performance limits for popular engineering systems such as heat engines and refrigerators, as well as the forecast the degree of completion of chemical process. The Kelvin-Planck statement and the Clausius statement are two expressions that is the second law of the thermodynamics. According to the Kelvin-Planck statement, no device on the cycle can receive heat from a single reservoir and produce a net amount of work, implying that no system can produce a net amount of work while operating on a cycle and exchanging heat with a single thermal energy reservoir. According to the Clausius statement, it is impossible to build a device that operates in a cycle and produces no impact other than heat transfer from a lower temperature body to a higher temperature body.
Hello, good day, doctor, and also fellow friends. So I am Teck Ling. I will be explaining about the procedure for this experiment. So you can see this is the apparatus. So we will need the kettle, beaker, weighing scale, or we call it as a balance, and then container, the bigger container, as well as a thermometer and also the stopwatch. So you can see this figure one is actually the schematic diagram of the experiment. So inside this big or we call the larger container, inside the larger container there is a small beaker. So in the small beaker actually contain the hot water, and then the large beaker contain the cold water. Okay, so this is the methodology. So at first we will be boiling the water in the kettle, and then the two different size of the container, one is the bigger and also the larger container. We will weight these two containers first, and then we will fill the larger container with a little amount of the cold water, and then the mass of the cold water is being weighted as well. And the smaller container, which is the beaker, will fill with the hot water. The hot water which is around 80 to 90 degrees Celsius, and the mass of the hot water was being weighted as well. After that, the hot water container will be placed inside the cold water container, as shown in the figure 1 schematic diagram of the experiment. And then the reading of both water temperature was recorded for every 1 minute until they reach the same temperature, which is the thermal equilibrium, while using the thermometer. Yeah. So the stopwatch will also use to calculate every 1 minute, so that we will record the readings of the temperature for every 1 minute. So that's all from me. I will pass to my teammate.
My name is Wan Izni Fadlila binti Azmi, and I'm going to proceed with results. So as we can see in this slide, for table 1, this is the table of temperature of hot and cold water for every 1 minute that we obtained in this experiment. So this experiment requires us to record the time for every 1 minute and temperature of hot and cold water respectively for every 1 minute. Why we record the temperature is because temperature can be defined as the measurement of average thermal energy of a substance, where this average thermal energy is actually kinetic energy of atoms and molecules in a substance. This kinetic energy can be transferred between substance by flow of heat. So in this experiment, we are focusing on the flow of heat, so that's why we record the temperature of hot and cold water so that we can see the relation of the flow of heat later. So next, we have the data here, which is a heat capacity of water Cp is equal to 4.187 kJ per kilogram Kelvin. Mass of hot water used is 0.1980 kg, while mass of cold water used is 0.8352 kg. For the calculation later, we will be using the energy balance relation, which is energy in minus energy out is equal to energy in the system. So since in this experiment we are focusing on the heat energy in cool water and hot water, so we have the relation here, which is the change of heat energy in the system is equal to 0 when it reaches thermal equilibrium state, where the change of heat energy in the system for this experiment is equal to change of heat energy in hot water plus change of heat energy in cold water equal to 0. Change of heat energy in hot water is equal to mass times heat capacity of water times T2 minus T1 of hot water, while change of heat energy for cold water is equal to mass times Cp times temperature 2 minus temperature 1 for cold water. M is equal to mass in kg, Cp is equal to heat capacity in kilojoule per kilogram Kelvin, while T is equal to temperature in Kelvin. Next, we have the graph of temperature of water versus time. We can see that the graph of hot water is in the gray line, while graph for cold water is in blue line. So, for graph of hot water, we can see it is decreasing with increasing of time, while the graph for cold water is increasing with increasing of time. We can see that we obtain the equation of graph for hot water is y equal to negative 1.069x plus 60.632, which means the gradient is in negative. It is because the graph is decreasing. As for the cold water, we obtain the equation of graph is y equal to 0.0397x plus 36.222. So we can see that the gradient is in positive. It is because the cold water graph is increasing with increasing of time. Okay, so for now we need to calculate the energy change of hot water. So by using the same equation as before, that the change of heat energy is equal to m times Cp times T2 minus T1 of hot water. So we use the mass of hot water, which is equal to 0.1980 kg times Cp is equal to 4.187 kJ per kilogram Kelvin, and T2 for hot water is 38, while T1 for hot water is 80. So, but we need to convert the temperature in Kelvin, so we need to plus the T2 and T1 with 273.15, and then we get the energy change for hot water is negative 34.82 kJ. The negative here means that the energy is being released from hot water. Okay, so for the last one is we need to calculate the energy change of cold water. So by using the same equation as previous in hot water, we use the mass for cold water is 0.8352 kg and Cp is same 4.187 kJ per kilogram Kelvin. And then for T2 for cold water is 36, while T1 for cold water is 28, but we need to convert it to Kelvin, so plus with 273.15 respectively for T2 and T1, until we'll get energy change for cold water is equal to 27.98 kJ. So this positive value means that the energy is absorbed.
Hi everyone, so my name is Zafran. I will proceed with the discussion part. Okay, for the discussion part, in which we need to explain the observation that we got from the experimental conducted, and also like the energy change and the relation with the second law of thermodynamics. For the first one, which is the observation of the experiment that has been conducted, we notice that we can obtain the tree graph from the experiment itself, and it shows us that the pattern of energy changes for both hot water and cold water, in which you can see after the 25 minutes of conducting the experiment, it shows that both hot water and cold water is actually they are achieving the thermal equilibrium, in which the temperature gradually meet and intersect with each other's line. Okay, and then for the next one, which is the energy changes and the relation with the second law of thermodynamics, from the graph itself that we come up with, okay, it depicts the energy transfer in and out from the system, in which it shows that the both system obey the first law of thermodynamics, which the total energy isolated system is constant. Due to that, it proves that energy can be transferred or transformed from one to another. However, it cannot be created or nor destroyed. According to the graph presented earlier, the gradient of each graph represents the temperature changes from the starting point till the end. From the first, you can compare the pattern of the hot and the cold water in transferring the energy by releasing and absorbing the energy from one and to the environment. The other things that we can pointing out is the gradient value for the second and the third graph, where the gradient value is higher for the second graph than the third one, in which it explains the second law of thermodynamics, as in the heat transferred from high to low energy. That's all from me. I'll pass to the next person. Thank you.
Hi, I'm Sri Nagendra and I'm going to conclude this experiment. So in conclusion, the experiment's objective is achieved and the first law of thermodynamics and the second law of thermodynamics is both applied. Both hot and cold water had an energy change of which 34.82 kJ and 27.98 kJ respectively. If the change in energy was zero, this will violate the first law of the thermodynamics. The discrepancy must be due to an error made during the experiment in which the beaker and the huge container were not properly insulated, causing energy to be lost to the environment. Heat was transferred from hot to cold water in this experiment until it reached equilibrium. This proves that the thermodynamics second law was being observed. That's all from us. Thank you.